Welcome. I'm Nicola Fusi. I'm a researcher in Microsoft Research New England in Cambridge, Massachusetts. And I want to welcome you to this talk, which is presented by the AutoML research community at MSR. Frank's talk is the second in our series this year on directions in machine learning, AutoML, and automating algorithms. For more information, including our speaker lineup and video archive, you can go to aka.ms/diml, written as DIML. So Frank is a full professor of machine learning at the University of Freiburg in Germany, as well the Chief Expert AutoML at the Bosch Center for Artificial Intelligence. He holds a PhD from the University of British Columbia and a Master of Science from TU Darmstadt. In the field of AutoML, Frank co-authored the ECML workshop series in AutoML in 2014 and has co-organized it every year since. He also co-authored the prominent AutoML tools AutoWeka and AutoSKlearn, won the first two AutoML challenges with his teams, co-authored the first book on AutoML, worked extensively on efficient hyperparameter optimization and neural architecture search, and gave a NeurIPS 2018 tutorial with over 3,000 attendees. Today, he's going to talk about neural architecture search, coming of age. This talk is going to be about 45 minutes long, and we will have a 15 minutes live Q&A after. The recording of this talk will be publicly available, but the Q&A will not be recorded as it's for attendees of the live event only. So feel free to write questions in the chat as you think of them, and Frank will either answer them live in the chat or we'll save them for the moderated Q&A. Thank you and enjoy.
Thanks, Nicolo, for the nice introduction and for inviting me to give a talk here. So my talk today is titled Neural Architecture Search Coming of Age, and I'm basically going to give a description of several different works in neural architecture search that I think are really cool and how the field as such is, well, coming of age. One quick note, all these slides are available at www.automl.org/talks. And all the references I have in the talk are hyperlinked. So if you get the PDF, you can get directly to all the different papers by clicking on them. All right, so to start off, let me mention that neural architecture search really is exploding. We wrote the survey in, well, end of 2018, published in 2019, when it was, still a manageable field. And the number of publications that came out in 2019 were already 4 times more than in 2018. And that factor already was there before. And this is 2016. Is when this paper Neural Architecture Search with Reinforcement Learning was published at ICLR by Sof and Lee. And that's really when neural architecture search hit mainstream. And since then, it's really exploding. However, neural architecture search is still in the process of overcoming some childhood problems. It hasn't fully come of age yet. So there was this ICLR 2020 paper, NAS evaluation is frustratingly hard, which showed that, well, just by playing with the different settings of your training pipeline, you can get better and better and better and better performance. So a total difference of something like 3% just by playing with your settings of the training pipeline, such as adding drop paths and cutout and auxiliary powers and more channels and using auto-augment and more epochs. And so this is 3% difference going from here to there. And the architecture space, well, that's just something like 1% different or 0.5%. So that doesn't shed a great light on neural architecture search. But nevertheless, neural architecture search has led to much better architectures being available now than previously. Another issue in neural architecture search is that while the community is quite focused on tables like this with performance numbers like this, and I would argue that, well, these numbers are just really incomparable due to this issue of the settings being really important. Because all of these different papers, where with these being reported test errors in the different papers, use different training code, different hyperparameters, different search spaces, different evaluation schemes. So this is really very incomparable, and just how good a performance you get on CIFAR 10 doesn't really mean much about how good is your meta algorithm, your neural architecture search algorithm. And I would very much advocate for disentangling these two. And that brings me to the overview. The first part that I'm going to talk about is actually about best practices and benchmarks for neural architecture search in order to really help the field completely come of age and be a scientific field with good principles. The second part is about speed up techniques for neural architecture search, because well, the original work by Sofan Lee with reinforcement learning, well, that used 800 GPUs for several weeks. And well, of course, that is not something that we can do on an everyday basis for all kinds of different problems in academia and not even in industry. So speed up techniques are very important, and this will actually really be the biggest part of the talk. There will be 4 different speed up techniques I'll talk about. Then I'll briefly talk about Auto-PyTorch, which helps us to actually jointly search in the space of neural architectures and hyperparameters in order to really give us off-the-shelf AutoML, so something that can be fairly hands-free. And finally, I'll briefly talk about an extended problem formulation where we don't search for just a single architecture, but for a whole ensemble of neural architectures. All right, let's jump right in and talk about benchmarks and best practices. The first benchmark that we introduced back then, 1 year ago at ICML, was NASBench 101. So this is a relatively small search space that we exhaustively evaluated in order to enable researchers to afterwards do work on neural architecture search, where if you would normally query the performance of a neural architecture, you now go and look it up in a table. And so the table lookup takes less than a second, and you can then run architecture search experiments on a laptop in minutes, rather than taking 800 GPUs for weeks. This clearly enables proper scientific research. Now we can do multiple runs, now we can do robustness studies and get statistical significance. And we can also do fair head-to-head evaluations by design, because, well, you don't have a possibility to actually tweak the training pipeline because, well, the values are just saved in the table. And, well, of course, the source code and the scripts are available for this as well, for anyone to start from it and continue. A few more details. So there we looked at 423,000 architectures. This is a very small cell search space, but it's still quite large in absolute terms, so 400,000 networks being evaluated. And the important thing is that this had to be done once, and nobody has to run these 400,000 architectures again. And this was really only possible with large-scale industrial resources. We did this project together with Google and used 4,000 TPUs for several months. So yeah, thanks for all that compute time. That was very helpful. Some things that we can do with such a benchmark is, well, actually properly compare different optimizers. And we did that in the NASBench 101 paper. And there we saw that, well, we compared hyperband and random search, SMAC, TPE, regularized evolution, Bob, and reinforcement learning. And noticed that, well, regularized evolution actually is better than reinforcement learning, is better than random search, but Bayesian optimization is here just as good as regularized evolution. And notice that the SMAC algorithm here that was actually published in 2011, and that outperforms RL that was published in 2016. But of course, nobody would tell the people, Sofan Lee in 2016, oh, can you please compare this against SMAC or compare this against these other 10 baselines? Because, well, 800 GPUs for multiple weeks, you can't run this many times. And even their own algorithm, they ran a single time, 800 GPUs for several weeks. Now, now that we have these tabular benchmarks, we can actually trivially run all of these algorithms many times. Each of the lines here is based on 500 runs, taking the mean of those. And yeah, we can do these scientific studies using these tabular benchmarks. So they're really extremely useful. There has been follow-up tabular benchmarks. One actually from my own group, where we took subspaces of NASBench 101 that have been fully evaluated, because NASBench 101 has this problem that, well, even though we had 423,000 architectures, we couldn't cover an entire search space completely, but we had a constraint that we would only allow at most 9 edges in this directed acyclic graph that describes the cell architecture. And if you try to use 10 edges or more, then, well, there's just no architecture evaluated for that. And so you can't evaluate one-shot models that would require evaluations of all the possible instantiations of the search space. And what we did in NASBench one-shot one is actually to look at subspaces of NASBench 101 that are fully evaluated and work for one-shot methods. And there we have 3 different subspaces that have respectively 6,000 and 29,000 and 363,000 architectures. So still quite large, and those work for one-shot methods, and that's why it's called NASBench one-shot one. At the same time, NASBench 201 came out by Juan Dong and Ying Yang. And their approach was a bit different. They actually came up with a new neural architecture search benchmark that had very few unique architectures, only 6,000 compared to 420,000. But their search space was very nice, very clearly aligned with the typical search spaces that you would use for one-shot methods. And therefore, it's very convenient to benchmark your one-shot methods. And what's also very nice is that they had 3 data sets. So you can do meta-learning experiments on this. And they have the entire learning curve logged. So you can do learning curve extrapolation and things like that on this data set. Now, one problem of all of these NAS benchmarks is still that they're too small to be realistic. Even this 423,000 architectures here is very, very small compared to larger search spaces that are realistic. And indeed, it has been shown that local search is actually state of the art for these tabular benchmarks, but performs very poorly on large spaces. So we're not quite at the point where we can really design our methods to work well on these tabular spaces and then be quite sure that they're going to work well on the real benchmarks. And here comes the first contribution that I want to talk about a bit more. This is an archive paper that actually came out today, and it's NASBench 301. And the new thing here is that this is really the first benchmark that's for a realistic NAS space, namely exactly the one of the DARTS paper. So this has 10 to the 18 architectures compared to the, well, 10 to the, how much is this? Less than 10 to the 6 here. So more than a factor of 10 to the 12 more architectures. And of course, the space is ridiculously large. We can't exhaustively evaluate in this space. And what we do rather is to actually fit a surrogate model rather than a tabular benchmark. So this works as follows. We just observe partial results. We observe a lot of different architectures in the search space. And then we fit a regression model to use instead of using a table. And this regression model can, of course, extrapolate to unseen architectures. Surprisingly, maybe at first glance, this can yield better estimates of the true performance than a tabular benchmark. And the reason for that is as follows. So tabular benchmarks actually still have noise. And they're typically based on only one or very few runs per architecture. And these runs, well, they're running SGD. SGD is a stochastic algorithm, and it yields quite different performance in different runs. So by just trusting the result of a single run, you're going to have an approximation error of the true underlying performance of this architecture. And if you view tabular benchmarks from a machine learning perspective, from a statistical estimation perspective, then basically what they are is they're models that assume complete independence of the performance of all the different architectures and only put all their eggs in the one basket of this one run or the very few runs for an architecture A that we saw exactly before. So when you want to predict for or look at the performance of our architecture A, then you look at exactly the run for architecture A and no other runs of similar architectures. However, we know that there is large noise in SGD, and we know that the performance of similar architectures actually is similar. So from a machine learning perspective, it makes a lot of sense that a model that doesn't make this independence assumption could actually do better and smooth out this noise. And precisely that's what we see here on the right. This is actually running on NASBench 101, where we have actually 3 evaluations per architecture, not just one. And what we look at here is the error that you would make if you just trust one run by looking at how different are the other 2 runs from this one run. So the 2 runs are the ground truth and the one run is the estimate. And we compare this ground truth to this estimate or to the estimate of a surrogate model fit on a different number of architectural runs with also just that one seed. And if you use that one seed for all the architectures and you fit a model on it, then your error is actually less than just trusting the single architecture, the single run of the architecture. And the break-even point is actually somewhere at about 15,000 architectures that you need to evaluate out of these 423,000. And then your surrogate model actually can generalize to architectures that are not in this training set. Right, so what did we do to build NASBench 301? We evaluated 50,000 architectures in the Dart search space, and we evaluated them using different optimizers because, well, we want to cover the whole search space roughly, and we did that using random search with 24,000 evaluations, and we wanted to cover good parts of the space. And we didn't really want to put all our eggs in one basket. So we ran different methods such as evolution, differential evolution, regularized evolution, TPE, bananas, combo, and a variety of different one-shot methods in order to collect the architectures that we would then evaluate, in order to really find the good architectures in this space. And because those are the ones that we will want to look at a lot when we do optimization in this space. We then evaluated a broad range of different regression models to fit this data. And what we found was that the best regression models were actually gradient boosting or graph convolution neural networks. So the graph convolution neural networks were better on some tasks and the gradient boosting better on some other tasks. And the details for that are in the paper. But the important thing to notice is that we can actually fit this data. And just like for NASBench 101, our estimation errors are actually lower than the error that's due to the noise in a single run of SGD. So even if we could fit a tabular benchmark on these 10 to the 18 different configurations, the estimated error of that would be higher than the estimated error of our model. And of course, that we can only show that for the architectures that are in our test set, but those are tens of thousands of architectures. So we trust it quite a bit. All right, what can we do with NASBench 301? Well, very similar things as with NASBench 101. We can, for example, benchmark different NAS methods. And so we can look at the performance of these methods on the true benchmark. And here we have one run. Or we can look at the performance on the surrogate benchmark. So here, evaluating an architecture takes several hours. Here, evaluating an architecture takes less than a second. And nevertheless, the evaluations, the qualitative results are very similar. So you see that random search, for example, is up here. It's not doing very well. Also not doing very well here. We can, for the surrogates, actually play time longer than for these, for the true benchmark. The true benchmark we couldn't run any longer because, well, actually this X scale here goes to 3 × 10⁷ seconds. That's 30 million seconds, which is, or 32 million seconds. It's actually more than a GPU year. And this is a single run of these neural architecture search methods. If you run them sequentially, we ran them in a parallelized fashion. Otherwise, you couldn't have done that at all. Here we can nevertheless say, oh, well, what if we ran this 10 times longer? We would get the following performance. Random search still wouldn't go anywhere. And well, RE just got better here, and then it would probably stay roughly there. We see that here bananas, Bayesian optimization with neural networks, does really well, and the same is reflected also in the surrogate benchmarks. TPE is not doing much better than random search, same in the surrogate benchmarks. DE is doing quite well in the end. This is the same as here, and this is just the continuation. So really very qualitatively similar results. The one difference here in the surrogate benchmarks and the true benchmark is that the performance is smoother on the surrogates. Well, and that is the case because we could only afford one run here, and we have many runs here and report averages. So overall, benchmarking on the surrogate is really something that looks very similar to the performance on the original DARTS benchmark. And we can do it quite cheaply now. The availability of these different NAS benchmarks combined with the note on NAS evaluation is frustratingly hard that I mentioned in the beginning, led us to propose these best practices for neural architecture search. So we very much encourage people to release their code, not just the trained architectures, but also code to actually do the training, to see what are the tricks that are being used in the different papers. As we saw in the NAS evaluation, is frustratingly hard. This can make up to 3% difference. Also releasing hyperparameters, releasing seeds, and so on. And then properly comparing methods that includes using the same search spaces, using the same NAS benchmarks. And using the same NAS benchmarks doesn't mean using CIFAR-10, but means using the same search space, the same optimization pipeline, and optimally the same hyperparameters. And then also, of course, the same data set. And the same training and validation and test splits and everything that belongs to a NAS benchmark. And then you can actually do fair apples to apples comparisons. And if you use tabular or surrogate benchmarks, then you actually get that part for free, and you can actually do these experiments really quickly, and you can get statistical significance on these benchmarks. I'm not advocating to only use NAS benchmarks for your evaluations. It sometimes helps to make sure that everything does transfer to the true benchmarks, but for all kinds of unit tests, for all evaluations, intermediate evaluations, and for the evaluations in the paper where we want to get statistical significance, I'm definitely advocating using a lot of tabular and surrogate benchmarks. And the third type of best practices concerns reporting important details, such as how much hyperparameter tuning actually went into a method and how robust it would be when you run it on new data sets and so on. So this checklist is an actual checklist that's available online. And the one suggestion that I would make based on this to reviewers is to actually de-emphasize the final results table on CIFAR-10 and other data sets, look a little bit less at that, and be aware of the many confounding factors that go into those final performance numbers. All right, so to summarize this first part, I think we've gone a long way towards actually building a scientific community around neural architecture search. We now have benchmarks that can be used really cheaply also by students who don't have access to any big compute. So this is really something where academia can do a lot now. We have this best practice checklist. We also organized the first workshop at ICLR on neural architecture search. And one thing that we're working on, where we have a first version, is a library of neural architecture search that's modular and extensible, and just implements all kinds of different methods and really enables clean empirical comparisons without confounding factors. Great. So much for benchmarks and best practices. And I'll now transition to the second part of the talk on speed up techniques for neural architecture search. As I mentioned, there will be 4 different types of techniques here. The first one is on weight inheritance and network morphisms. So network morphisms are operators that change the network structure, but not the modeled function. So that means for every input, the network yields the same output as before applying the network morphism. So you have a network, and then you put in a layer that makes this one, and say this layer here is just an identity mapping, and then the function that's computed by this modified architecture is still the same as before. And you can use these network morphisms in neural architecture search algorithms as operations to generate new networks that you then don't need to train from scratch, but for which you have pre-trained networks available that you can then just fine-tune. And this allows doing fast architecture search as follows. So you start from some model that has a certain performance, and I'm just showing here 2 large layers and 2 small layers, and it has a certain performance. And you apply different network morphisms, for example, making one layer wider, adding a layer, and maybe adding a skip connection. Because these are network morphisms, the performance is going to stay exactly the same, 82%. Then you do some fine-tuning, and the performance changes. And then you simply pick the model that has the best performance and iterate this process. And that actually allows you to do surprisingly fast architecture search through these local operations. So something like architecture search in 12 hours on a single GPU. One issue with this, however, is that the network morphisms only ever make your architecture larger. And you're never going to get small architectures with good performance. So in order to get those, we had this follow-up work on at last year's ICLR on efficient multi-objective architecture search through network morphisms. So here we want to trade off, for example, the network size versus its error. And we also had different measures in the paper, such as the number of flops and multiply add and the size I already had here, and also performance on different benchmarks such as CIFAR 10 and CIFAR 100. So the largest experiment we had actually had 5 objectives. And we're interested in a Pareto front, in this case here of 2 objectives, the number of parameters, and the validation error. And we initialize this with some default networks, one architecture here, one there, 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 and get this Pareto front where all the points above are dominated by a member of the Pareto front. So for example, a point here would have a validation error that's worse than this point and would have a number of parameters that's worse than this point. So this we don't need to care about. But all the members of the Pareto front, those are the models we would give to the decision maker and say, well, these are your options. These architectures are not dominated. And what we do here is evolve a population of Pareto optimal architectures over time. So we start with this generation, with this population, and over time, we actually get better performance, so lower validation error, and we also get a lower number of parameters. So we push this Pareto front from the first generation over time to the lower left and do proper multi-objective optimization. The resulting algorithm is called Lemonade for Lamarckian evolution for multi-objective neural architecture design. The Lamarckian part, that is the inheriting the weights from your parents. And this algorithm is still cheap. It takes something like a week on 8 GPUs. Well, relatively cheap for doing multi-objective optimization. All right. So far for the network morphisms, just to mention that, of course, you also can compare the resulting networks to other mobile-sized networks. And here we have the Pareto front of Lemonade compared to NASNet, this work on reinforcement learning for neural architecture search by Sof and Lee, and also different versions of MobileNet. And you get better performance. And in particular, compared to NASNet, the search is 35 times faster by using these network morphisms. the same. Also, you also get transferred to ImageNet. So no big surprises there. All right, so this was weight inheritance and network morphisms. The next speed-up technique I want to talk about is about weight sharing and one-shot models. And the most popular approach in that domain is the DARTS algorithm. DARTS stands for Differentiable Architecture Search by Leo et al., also at ICLEAR 2019. And this works as follows. So you have this discrete architecture search problem where you have operations on the edges, and you want to choose between different operations for each of these edges. In particular, you have this option, the red operation or the green or the blue, for example, 3x3 conv, 5x5 conv, max pooling, etc. And what DARTS does, it relaxes this discrete NAS problem where you only can choose one thing to say, well, I'm just going to use all the different operations between these edges, and I'm going to put weights on them. So that yields a mixed operator between node I and j that is just a weighted sum of the operations, of the individual operations, and the weights are encapsulated by these alphas. So the alphas are these architectural parameters, and then you can actually go and use gradient-based optimization in order to optimize these alphas, because the alphas are continuous values. And so you solve a bi-level optimization problem. You look for the alpha that gives you the minimal validation loss. When you combine it with weights that are optimized for this particular alpha. Weights optimized for this alpha by optimizing training loss. So that is a typical pipeline for hyperparameter optimization in neural architecture search. We look at the validation error of architectures that whose weights are trained on the training loss. And so that's a natural formulation. That's bi-level optimization to find the architectures that give you the best performance with these optimized weights for them. And that goes from here to there. So some of these edges then become a lot stronger, and some of these edges become much weaker. And the last step in DARTS is to actually then discretize each of these edges again and drop the least important parts. So the lowest alphas, the edges of those just go away, and only the strongest alphas remain. And then you have just a single architecture, not this one-shot model anymore. All right, so that's a DARTS approach, and this is very popular because, well, you can actually solve this bi-level optimization problem by just doing a gradient step on the alphas, followed by a gradient step on the weights, followed by a gradient step on the alphas, and a gradient step on the weights. So a very simple algorithm. There's no proofs of convergence or anything, but it actually works in practice to find good architectures and weights. And because of its simplicity and because the code is available, and this has actually really had a big impact in neural architecture search. Now, a few things we did with DARTS is we first actually had an application tuning a vision pipeline for depth from stereo, where we have a left image and a right image, and we just want to get this ground truth image. And well, actually, this is not ground truth. This is our result. So very nice results that we can get by DARTS. And in particular, we reduced the endpoint error on Zintel by 10% from the previous state of the art. So quite nice improvements in the previous state of the art. This is work together with Thomas Brox's group here in Freiburg, who has been working on depths from stereo for several years, and whose students really are experts in this, and we could nevertheless improve the error by relative 10%. So that goes to show that DARTS sometimes really works and is very nice, but DARTS also has really bad failure modes. It often fails horribly, returning only degenerate architectures, so only skip connects, only parameterless architectures. And in a paper at this year's ICLEAR, we actually showed that this behavior consistently for 12 different neural architecture search benchmarks. Every single time we got only skip connections or only parameterless connections, and that of course is very bad if you want to think about using this in the inner loop of an AutoML system. You can't have this sort of behavior. So we next looked at why this happens, and so it turns out that, well, the validation error here on the left, that actually shrinks over time. That's not the problem. Even though this bi-level optimization, there's no guarantee of this alternating SGD that this works. That actually does work. The issue is that the curvature in the space actually increases, and you're running into sharp local minima in the architectural space. So here on the right, we're actually plotting the dominant eigenvalue over time, and we see that that's actually going up as the test loss is going up over time. So first the test loss is going down nicely, but then over time it's going up. And this is because, well, we're going into these parts of the space of high curvature. And then if you recall what DARTS is doing, well, it's doing this discretization step. So that's actually a sizable step in the architectural space. And if you have high curvature, then making a large step in this architecture space, then that actually, of course, gives you really bad performance. And so that's where the performance loss happens. It's in this discretization step because you have high curvature in the local area that you're ending up with in the optimization. And the solution is to, well, avoid this high curvature, either by early stopping or by adding some amount of regularization using kind of any of different methods. We tried L2 of the inner objective, and we tried scheduled drop paths. Both of these works. Both of these avoids a high curvature and leads to much better performance. So here is DARTS on CIFAR 10. It's actually tuned nicely. It works. But as soon as you just go to CIFAR 100 with the same code, you get very bad performance. And this robust DARTS gets much better performance. SVHN, similar story. PTB, also similar story. And other teams have also run this on ImageNet afterwards. We didn't have the resources for that, but got very substantial gains in the ImageNet architecture by using our robust DARTS. And there was also a nice follow-up paper that I wanted to mention because I quite liked it, that also proposes another type of regularization that specifically looks at the perturbation. So it's a perturbation-based regularization that either just adds random noise to in the architectural space or adversarial steps, and that yielded even nicer performance. So here's a plug for this paper. Very nice. All right, so this was weight sharing and the one-shot model. Next, I want to talk about meta-learning, so learning across data sets. And in this space, Chelsea Finn has done a lot of very nice work and, for example, proposed this model-agnostic meta-learning that has, so this inner task where you have a task where you compute a loss and you update your task weights with SGD. But then there's also this outer loss where you update your meta weights that where you try to find an initialization of networks such that if you do a few inner task optimization steps, you get good performance for different tasks. And how can you combine that with neural architecture search? Well, one related work that by Kim et al. Would be to simply put neural architecture search around this, and that works because, well, there is an architecture in here, and you can, well, just do a search on that neural architecture. However, that is getting quite expensive, and what we did instead is we actually merged the architecture optimization in here and in here. So in the outer loss, we update the meta weights and the meta architecture. And then for the task at hand, we actually do fine tuning of the architecture together with fine tuning of the weights. And that approach called meta-NAS actually is much cheaper than this prior work and yields clear new state-of-the-art results. So here's a table from the paper that's sort of the table reviewers want to see, with completely incomparable methods. Well, not method, but completely incomparable pipelines. So different training pipeline and different hyperparameters that we still do best because we did a lot of engineering for it. Here is the more scientifically honest comparison with the same training pipeline and the same hyperparameters for, well, this original reptile algorithm, and then reptile with the neural architecture search wrapped around, and reptile with the neural architecture search together with the individual weights. And yeah, this approach is also 10 times faster than this approach and yields the best performance in most cases, especially if you run it for longer than actually in all cases. It yields the best performance. All right, so that's what I want to say about meta-learning. And then the last speed-up technique I want to mention is multi-fidelity optimization. So the key idea here is to use cheap approximations of the black box, such that the performance of these on these cheap approximations correlates with the performance on the expensive black box. You could have all kinds of different cheap approximations. For example, you could use subsets of data or fewer epochs of iterative training algorithms, or you could downsample your images, use shorter MCMC chains and Bayesian deep learning, or in deep reinforcement learning, you could use fewer trials. The simplest method you could use here is successive halving. This is shown here on the right for a wall clock time as a budget. It's a very simple algorithm that basically says, take a bunch of different configurations, architectures or hyperparameter settings, it doesn't really matter. Train them for a while, look at the worst half and the best half, and the worst half you just cut off, the best half you continue running. And then you double the budget and look here again, cut off the worst half, let the rest running, double the budget, cut off the worst half, let the rest running, and you end up with very good architectures that you have put quite a bit of time in, but you haven't put all this time into these weaker architectures, and you've saved a lot of time. So that's a very nice, very simple approach. There are many more complex methods, including some by ourselves, combining this with Bayesian optimization and so on. But in the end, actually, the combination of successive halving or its extension of hyperband that I would advocate is to combine this with Bayesian optimization in a very simple manner, where you basically use hyperband, but you don't, or successive halving, but you change one thing, namely which configurations you actually put in. Whereas successive halving in the original version actually looks at random configurations. We sample these with Bayesian optimization, and that gives much better performance for longer running runs. So just one quick showcase of multi-fidelity in action. I showed this result here earlier where we used NAS with darts to improve state-of-the-art performance on Zintel by 10%. Afterwards, we actually applied Bob to this and got another 10% reduction on top. So, and this is at a runtime that's, yeah, definitely less than an order of magnitude than standard black box methods. All right, going on to the last 2 points, which are relatively short. So Auto-PyTorch is a method for joint neural architecture search and hyperparameter optimization. And it's kind of follow-up of our first work on AutoNet, which actually did joint neural architecture search and hyperparameter optimization back in 2015. And actually, to the best of my knowledge, was the first automated deep learning system that won a machine learning competition dataset against human experts. So there it got area under the curve of 0.9, whereas the best team of human experts, and there were more than these 10, actually only got 0.8. And they had something like 2 months in a Kaggle style challenge to tackle this data set. So that was already a quite nice showcase back then. Back then, this was relatively slow with black box optimization. And in the meantime, now we're actually using multi-fidelity optimization, and we're using meta learning to warm start this process across data sets. And this is work in an archive paper earlier this year. So yeah, and actually this is also open source, and we haven't been pushing this for a long time. So, but given that we've only been pushing this for about half a year, I think it's finding a big following already. So in brief, this is the design space for Auto-PyTorch Tabular. For tabular data, we use a so-called shaped ResNet. So and we also look at MLPs, where we basically configure the number of blocks and the number of groups as you would for residual networks. And well, residual networks are typically used for convolutional neural networks, but there's nothing that is holding us back from also using residual connections for tabular data. And we do, and it actually helps. It's quite a bit better than the MLP nets. So the design space is relatively small. We only have something like 12 architectural choices and 12 hyperparameters. So about a dozen each. And here's how we search this. We do multi-fidelity meta-learning. So multi-fidelity optimization with Bob. We have as budgets the number of SGD epochs. This is 12, 25, or 50, so actually relatively small. And so we can only get something like a speed up of 4 because the cheapest budget is only 4 times smaller than the most expensive budget. But nevertheless, we actually often get this factor of 4. Sometimes only in the beginning. Sometimes we get overtaken in the end by optimizing only on the full data set. But sometimes actually even after a long time, Bob is still quite a bit faster than black box BO. And the more important contribution here is to actually also use meta-learning. So to initialize the search with complementary configurations that cover a lot of previous data sets. So what we did here is to look at 100 different data sets and look at what are the instantiations of Auto-PyTorch that would do well on these previous data sets and make sure that we get a set of complementary configurations using our greedy submodular optimization. And we also compared this against the simple portfolio where we would just put 100 configurations that did best on each of the previous data sets. And sometimes the simple portfolio is just as good as our submodular built portfolio, and both of them are a lot better than Bob. And sometimes, well, this smarter way of building the portfolio is actually very important compared to this simpler way. And in all cases, definitely the warm starting helps a lot to be orders of magnitude faster than just Bayesian optimization with multi-fidelities. Here's an evaluation against other AutoML frameworks. And here we do really well compared to AutoKeras and AutoScaLearn and HyperOptScaLearn. And we're doing further evaluations right now on the OpenML AutoML benchmark. So that's 39 data sets that were collected by different people. And we also do an evaluation against AutoGluon with the AutoGluon team in order to make sure that everything is fair in that comparison. One might wonder whether the same approaches also work for image data, and actually, yes, they do. So we evaluated this on NASBench 201, where we have 3 data sets, C410, C400, and downsampled ImageNet. And so we really only have 2 data sets that we can train on, meta train on, and 1 to meta test on. And even though we only have data from these 2 previous data sets, the warm starting really helps a lot. The multi-fidelity optimization here doesn't help because there's actually quite weak correlations across budgets in NASBench 201. But the warm starting here gives you 1 to 2 orders of magnitude speed up over, yeah, just doing Bayesian optimization or Bob by themselves. And actually, if you compare this to gradient-based NAS, it actually is something like 4 times faster to reach 90% on CFAR. So doing this multi-fidelity meta-learning actually gets you to the realm of being extremely competitive with gradient-based neural architecture search. And here you have the advantage. You can trivially put in a few hyperparameters and optimize them exactly the same way that we optimize also the neural architecture. All right. That brings me almost to the end. I just have, I think, 3 more slides about this extended problem formulation on neural ensemble search. So here, the motivation is as follows. Ensembling often improves the performance of neural networks. We all know that. And recent results also actually show that if you use an ensemble of a neural network, just 10 copies of the neural network that were just 10 instantiations of SGD and the different minima found, that actually gives you very nice predictive uncertainty and also robustness to distributional shift, and in particular better results than all the Bayesian deep learning methods out there typically. And but that seems suboptimal, because diversity among the base learners' predictions is really key for strong ensembles. And achieving diversity through different architectures hasn't been studied so far. So all that they did is take a single good architecture and take multiple copies of that. And what we propose is to actually use neural architecture search to search for strong ensembles of diverse architectures. So this is not directly encoded that we want them to be diverse, but in order to be complementary and give good ensemble performance, they automatically become diverse. So here I visualize that different architectures actually give you diverse predictions. So here's 5 different architectures and their predictions in a t-SNE encoding. And here is several different architectures found by neural ensemble search. And here's on the same problem, the deep ensemble. So this is a single architecture, a single good architecture. And we see the diversity here is much smaller in the predictions than the diversity in the architectures coming from NES. And this results actually also in better performance, because greater diversity helps to reduce errors. So here we look at the neural ensemble search as the number of networks evaluated becomes larger and larger. So as the search progresses, with 3 architectures in the ensemble, 5 architectures, 10 architectures, and 30 architectures, and likewise for deep ensembles based on the architecture found by DARTS and the architecture found by AmoebaNet, which is actually quite a bit larger than the architectures that we look at. And nevertheless, we can do quite a bit better than AmoebaNet, especially when we allowed many members in our population because of the diversity in our ensemble members. We can also directly optimize for robust predictions under data shift. And if we do that, then we actually become very robust to these data shifts, and we get very nice uncertainty estimates, and much better than deep ensembles, and also actually achieve state-of-the-art performance for robust predictions under data shift. All right, that brings me to the end. The takeaways I would like you to take away with you is that neural architecture search is really coming of age. There's a lot of cool stuff happening. There's a scientific community forming around neural architecture search that everybody can become involved in now. There is open source, there is benchmarks and best practices. There's a ton of different ways in order to speed up neural architecture search. So we don't need huge compute clusters anymore in order to do interesting research. And this also becomes practical now. So Auto-PyTorch really tackles joint neural architecture search and hyperparameter optimization. And well, you can also apply this in this extended formulation to find great ensembles. There's links to code, and there's a book on neural architecture search. With that, I would like to thank you very much for your attention, and also many thanks to funding sources and especially to my fantastic team. So thanks a lot.
Great, thank you for the incredible talk. It's a head-spinning amount of work that you put in there, and it was really interesting to see like the different aspects. You touched on very interesting aspects, from NAS work to hyperparameter optimization to joint NAS and hyperparameter optimization to meta learning to ensembling with NAS. It's super interesting. We had quite a large amount of questions that you I guess you didn't get bored during this talk in replying to all of those. It was actually quite frenetic, I think, to stay up to speed with what was coming in. But one thing that I wanted to do, and while people can keep throwing questions in the Q&A. I'm keeping an eye on it, and if they have them, I'm going to ask them live. But in the meanwhile, we have kind of like a block of questions on NASBench 301 that came in from different people, and I have my own, and I want to kind of bring them all in into one single question. So let me start with a string of questions from Dibadip today, who's asking about, in 301, 50,000 architectures are used for training the predictor, it's beyond the 25,000 randomly sampled architecture. You also add the pathway of popular NAS algorithms. Doesn't this make the predictor biased? And I think you answered in the chat, but would be useful, I think, because it's an interesting question to answer here as well. And then I'm going to ask a follow-up, and then a follow-up, and then a follow-up. Yeah. Okay,
great. Yeah, those are very good questions about NASBench 301, and of course I only talked about it for a few minutes, and we have a lot of experiments in the paper that answer a lot of these questions. It is a good point. We can't cover this space exhaustively, well, because it's 10 to the, I forgot the exact number, 40 18? Or 10 to 18 like in this case only, and another version has 10 to the 23. But so it's huge. We can't possibly do this. And so we're going to miss some, and we're really trying to think of what are the best architectures to evaluate in order to cover our basis, in order to cover all the different parts that we need in order to make a good NAS benchmark. And a good NAS benchmark, of course, I think needs to be kind of good in the interesting areas. NAS optimizers try to find good architectures, and I think that's why we should actually try to make particularly good predictions for the good architectures. For the bad architectures, well, one could argue, for example, for these robustness issues of darts, it's really important to actually also cover that, and to not just say, well, that's a relatively bad one, but to say that that's a really, really bad one. And that is a failure mode that we know. And because of that, we actually did put, and I didn't talk about that, but we did put additional training data in there from all kinds of architectures that are derived from other architectures, and then add in more and more parameterless operations. So more skip connections, more more max pooling, and so on, in order to make these architectures worse and get better training data for that. And we actually still need to do an ablation study to see how much that helped, but I'm sure that helped for these very bad architectures to show that they're very bad. I don't think that without these really bad architectures, we would see any differences in the rankings of the different NAS optimizers. And I think that's one of the things that well, people tend to do a lot with NAS benchmarks is to rank different methods. And also in terms of the bias, well, it's biased in the sense that you make good predictions for the architectures that you trained on. It's not biased in the sense that you're predicting the architectures that you trained on to be good. So you're actually getting better for those. And for others that you haven't trained on, well, your uncertainty is larger, and you might potentially make larger errors if there are some parts of the space that nobody has ever considered and that we don't have training data on. And there, the extrapolation error would be larger, and the uncertainty is larger. We also have uncertainty estimates.
I see. Yeah, so that's interesting. So you touched on this in your answer, but there is a follow-up question where which was asking, if we bias the population to the good architectures, then the predictor may extrapolate good performance in areas where the architectures are actually bad. At a higher level, I'm wondering if we can move away. This, I guess, is the second part of the question. Can move away from CIFAR 10 and want to create, say, 301 for dataset X. How should we go about selecting architectures?
Yeah, so we're trying to come up with the best way to select architectures in order to cover our bases. And I would actually be very interested in people knowing other failure modes that we could and should actually cover in our data collection. And I think one part that's really important is that we should always be open to add additional data to the benchmark. And because of that, we set up versioning, and we're not just going to change the benchmark without telling anyone, because then we get incomparable numbers between different papers. But papers should then compare on like version 1 against version 1, version 2 against version 2, and or 1.73 against 1.73 in order to train on the same architectures. And I think we thought of everything that we could think of, and I'm relatively confident that we thought of most things. I can't say that we thought of all, and there might well be some things that we haven't thought of, and that there might be ways of coming up with other architectures that are really interesting to train on. Actually, one thing that we still do want to do is that will take more compute again, is to actually run basically run an optimization on the surrogate and look at the architectures that are predicted to be best by the surrogate, and then evaluate those, add them back to the model, iterate this in order to sort of converge, in order to verify that the model is not predicting anything to be far better than it actually is. We don't have any indication that that is happening, but we haven't run this iterative process mostly due to compute issues. But we're still
I guess
to do more.
That was one of my questions as well. Like, could you so if we are going to ask more questions about the fidelity and 301 and the surrogate model, but in theory, if the surrogate model is that good, couldn't you use that as a prior in a GP, for instance, to then do Bayesian optimization, and then you can basically, probably reduce the sample complexity quite a bit, right? Because if the surrogate is so good, you can do a double surrogate in some sense.
Yeah, well, I mean, of course, you could cheat and say, well, I'm gonna define a new algorithm to search on the Dart search space and put in 50,000 data points on the Dart search space. I think that's
I don't know if
you don't want to do that. If you then go to a different search space or a different benchmark and so on, well, then that's more meta learning, and that's fair game. It's just we did a lot of the data collection that you would need to do in order to do proper meta learning. We've only done it on one data set, again, due to compute.
Yeah.
But I didn't want to give the impression at all that, well, NASBench 301 is the be-all and end-all benchmark. But I think it will be the first surrogate benchmark in a long line of different surrogate benchmarks, because, well, we have just been tying our hands behind our back to stick with these tabular benchmarks where we need to actually evaluate everything. And well, there we have seen that there's also errors that you make by actually only having very few evaluations, and that you can actually, from a machine learning perspective, just do better if you actually use machine learning rather than actually just use a lookup table, and you exploit the fact that, well, you have smoothness across architectures and so on.
Yeah, what I was suggesting. I don't know if it would even count as cheating if you evaluate 50,000 darts architectures, right? In some sense, when you're designing a search method, a new search method, you do run a bunch of trials. Maybe you don't evaluate as many as 50,000, but you do run a bunch of trials, then incorporate that knowledge into your design of your search method. It wouldn't be a super, and also then people use these search spaces for years, like, Dart,
Yeah. I mean, if you did do this on the Dart search space for CIFAR 10, then, well, I would argue you're looking at your test data during training, right? Because I can give you in 0 seconds an awesome architecture.
That's true. I guess if you don't go the full 50,000, if you do like 300, that.
Yeah, and I mean that's the sort of stuff you can use that as the initial design for your Bayesian optimization or something like that. You can get that for free. That makes perfect sense. I mean, not for free. You should count the runtime, and we did of course log the runtime that it took in order to run these. So you can on the x-axis put the simulated walk time.
Yeah, no, that's great. There was a follow-up question by Neil Tannenholz, who was asking, could you comment on the fidelity of the surrogate model? Given the cost of exhaustively evaluating the Dart search space is prohibitive, sparsity is clearly unavoidable. Nevertheless, 50,000 architectures is less than 10 to the 18. As a corollary, if such a sparse prediction task can be accurately performed, does it suggest that much of the Dart search space is redundant?
Well, I think redundant is a harsh word. There is regularity in there, and there's smoothness. We also looked at some some experiments that I didn't talk about, looking at if you increase the number of mux pooling, if you increase the skip connections, and there are regularities. And it typically, well, it only gets worse the more parameterless operations you put in, except a few skip connections are useful. And yeah, you can call that redundant. You can call it the performance factors into smaller pieces that you can use in order to actually make these predictions. And that's not too surprising, I find. I mean, otherwise we as humans couldn't really make sense of these spaces, and we can use models like this in order to actually find these regularities. And then, of course, we only find them in the model. We only find them in these 50,000 data points. Then we actually also need to go and verify that these hold on test data that we haven't used in order to come up with just regularities. But I think that's also pretty cool. And actually, one thing that we did since taping the talk, we looked at this local search stuff from Colin White that sort of motivated going away from these really small tabular benchmarks, because it did really well on the small ones and not on darts, and found that it didn't do well on darts in the first few iterations. That's all that Colin actually had resources to run. And afterwards, it actually did really well. And now we're running this on the true Dart space, and it looks like it's also doing really well there. So we can use these benchmarks in order to actually come up with hypotheses that we can then test in real life on the real benchmark. And we kind of also need to close the loop and do that, and not only stick to surrogate benchmarks.
Yeah, no, I agree, but that's really interesting. I didn't know this after the taping discovered. That's kind of interesting. I guess I have one question, and since you started talking and answering other questions, I've kind of gone back a little bit from it. But hearing your talk, I was curious, what's the objective function? What's the loss you use for your surrogate, to evaluate your surrogate or to train it? Are you looking at root mean square error? Are you looking?
Yeah, just well, root mean squared error, and also Kendall's tau and correlation coefficients.
Okay, so that was kind of my question, because my prior was you really care. So probably with NASBench 101, since NASBench 101, you've done a lot of looking at the histogram, at the distribution of the performances of different architectures sampled from the space, and you will probably have noticed that there is an accumulation around an average performance that is pretty bad. It's relatively good. All these architecture search spaces are pretty good, I would say, unless you fall in some kind of really bad all skip connection kind of architecture pit-hole of despair. But then the high end is kind of like a very thin tail to the good architectures. And so my question was, if you use the root mean square error to evaluate the accuracy of a surrogate model on such skewed data, you're probably not capturing the fine-grained things that a practitioner would care about. And so maybe I was thinking a ranking loss, like a normalized discounted cumulative gain, would work better.
Yeah, that definitely makes sense, and we've also thought about that. Actually, Bananas used a sort of ranking loss in their predictive models. So yeah, we thought about actually putting that into our surrogates, and it's true, we could also put that into our evaluation. We haven't done that. It's a good point.
It would be super interesting to see, and I guess, but the reason why I changed my mind after you started talking is because you were talking about the generation in the Dart search space, where you start or the search algorithm rather, where you can just start filling the architecture with skip connects, and that metric wouldn't really capture this. So because you kind of care about the very well high performing architectures and the very badly performing ones, and DCG would have to do it, reversed.
Yeah. So what we did do is some qualitative analyses like this. Like for the real architectures, look what happens if we add more skip connections, and then look in the model what happens if you do that. So these more qualitative analyses, but in terms of the quantitative analysis, I think doing the ranking loss absolutely makes sense. I forgot one thing just to say about the sparsity of the search space. So I mean, if you just think of these search spaces are not very, very high dimensional, right? And if you have, I don't know, 30-dimensional data and you have 50,000 data points in data science, nobody would say, oh, it's very hard to predict something in there, right? This should definitely be possible. And there's also this Open Graph benchmark where, they're collecting predictive tasks with graphs. And we're talking to them to actually get our data set in there to also get other people working on it. And there's lots of graph neural networks out there that are looking at performance prediction for NAS. And well, this is not the only one. And so I think that it's a pattern that there is predictability there for sure.
Super interesting. I have, we're actually at time, so I'm going to hold my question for when we meet later, because this is a virtual visit after all. All right, and I want to thank you again. This was an awesome talk, and it's going to be available, I think, on our YouTube channel. I feel like an influencer saying this, but we do make this available. So thank you again for virtually visiting.
Okay. Thank you very much for the invitation and for the opportunity to speak. And thanks for all the awesome questions in the chat. They were great.
All right. Thank you. Bye-bye.
Thanks.